Okay. Back to Dirichet's theorem. Does anybody remember what we're doing?
We just split up
Yes.
the sum.
Yes.
Yeah.
Yes. So we use the Fourier inversion to right, the thing that we're trying to study is this, where P is congruent to L mod Q. Right? We're trying to show that this thing is infinite, right? We show this thing, well, this will help us to show that this thing is infinite, right? We're trying to show that this thing is infinite by looking at this thing, right? And then we take this, we do Fourier inversion on it. We see that it's equal to like summation over all characters of something like this, summation P over all P, right? And then we break this thing into two parts, right? One of which is with the trivial character. One with the trivial character, we see that we can show that thing tends towards infinity as s goes to 1. And then so the thing is to show that the sum over the non-trivial characters is bounded, right? If we can show the sum over the non-trivial characters is bounded, well then we've got an infinite thing plus a bounded thing. So it's infinite, and then that will allow us to do it. Okay, so that's the idea, right? And so we have these things called L functions, right? The L functions, what are the L functions? You guys remember?
They have to do with the characteristic function and summing.
Yeah. So you have these not characteristic, but character functions. Yeah, character functions, and we look at the sum over all. Sorry, x sub n, right? Yeah. The sum over from n equals 1 to infinity of the Dirichlet character over n to the s, right? And so, right, if this were 1 over n to the s, we would have the zeta function. But what we have here is rather the Dirichlet character. Remember what the Dirichlet character is? Yeah, the characters are functions from G into S1, and then this is an extension to the entire to all the integers, right? It's like a periodic extension to all the integers of that character, and we're going to sum it over that. Okay. So yeah. So right. So remember the goal. So we have these guys, L, chi, S, right? The Dirichlet L functions, right? And then the goal that we're trying for right now is to get a product formula for the L functions that's analogous to the product formula for the zeta function, right? So we want to show that for s bigger than 1, that that this thing can be expressed as an infinite product, right? N from 1 to infinity. So infinite product 1 minus chi p over p to the s, like this thing, right? So that's the goal, to get write it backwards, s chi, to get this product formula, and then remember we're going to basically do something parallel to the to how Euler used his product formula to show the infinitude of primes, and that will do it for us. But we'll need to apply the logarithm, and so we needed to do all this work with the logarithm, with the complex logarithm. Okay, so that's where we are. I hope that's not wasted time. Okay, so we want to show so the theorem we're trying to prove now is the product formula. Right? We want to show this is true, and the first thing we do is just observe that both sides converge. So 1, because this thing if we look at it, if we look at the absolute value, right? If we look at this thing in terms of absolute value, well, that's controlled by summation 1 over n to the s. I mean, that equals summation 1 over n to the s, and we know that that converges, right? Because s is bigger than 1. Okay, so that's easy. And then for the right-hand side, we did some work last time that showed that as long as this thing converges it suffices to show that summation this thing converges absolutely. Right, we had this result on the convergence of infinite products, and again, this thing converges absolutely for exactly the same reasons. Right? When you take the absolute value, you get 1 over p to the s. Well, that's controlled by 1 over n to the s, summation 1 over n to the s. Okay, so convergence is easy, and so now what we want to do is we want to show that the difference between these two terms is 0. Right? Can be made as smaller than any epsilon. Okay, so so we're going to do this by introducing a bunch of intermediary terms. Basically, we're going to go crazy with the triangle inequality. So find the triangle inequality. We're going to recognize this as bounded by a bunch of other things. Okay, so by the triangle inequality, the left-hand side we can bound as okay, so we're going to take first the difference between so for any integers, positive integers n and an m, we're going to throw in just a truncated sum. Oops, it's 1 to n. Yeah. Okay. So we throw in a truncated sum. Of course, we have to put that truncated sum back in. And we take the difference between that truncated sum and a truncated product here. So we take this product and we truncate it so that we're summing over primes where the primes are smaller than capital N. Okay. I think I'm going to run out of space, so let me. Oh, that's okay. I'll just continue from there over to here. Okay. This is where I wish we had a big board. Hey, Jaden. Good morning. Okay, so we are trying to show the product formula for the Dirichlet L function. And we're just going to use the triangle inequality. Right, we're trying to get that, the L function can be expressed in this product form, and we're going to use the triangle inequality. Okay. So, okay. So, right. So we express this as Jim. If you don't mind, would you not use your computer today, if you don't mind? Is that okay? Do you take notes on your computer?
Yeah.
Oh, you do? Okay. Go ahead then. Sorry.
I can.
No, it's all right. It's all right. Just no. Go ahead.
Okay.
Go ahead. I'm sorry. Yeah. No. Okay. Okay, yeah. Okay, yeah, you're good. You're good. Okay.
Are you sure?
Yes, yes, I am. Yes, I am. Okay, yeah, okay. So, right, we're going to, use a triangle inequality. We take the difference between this and a truncated sum. We take the difference between the truncated sum and a truncated product. But we truncate the product in another way. We take the geometric series for this and truncate that. Okay, so we express, we take an approximation of this as well. So this will be 1 plus chi of p over p to the s plus chi of p of m over p to the ms. Okay. Yeah, okay. Okay, plus that latter term, so p in prime, p less than or equal to n, 1 plus chi of p to b plus p to the s, excuse me, plus chi of p to the m over p to the ms, right? And then we take the difference between that and now the actual truncated product. So p in p, where p is less than or equal to n, 1 over 1 minus chi p over p to the s, plus the difference between the truncated product, and the actual product. Please, and that's it. Okay. Okay, so we just put in a bunch of intermediary terms so that we can, over which the differences we can get control, right? We approximate this by a truncated sum. We approximate the truncated sum by this thing, right? Et cetera, et cetera. Okay. Okay. So so we want to show that we can make this this quadruple sum as small as we want. Of course, some of it is easy, right? This thing, right, as n goes to infinity, this converges to that, right? So we can make this as small as we want, right? Similarly, as n goes to infinity, this converges to that, right? So we can make this as small as we want. We don't have to worry about those terms, right? Let's see. This term as well, right, as m goes to infinity, right, as m goes to infinity, this term turns into this term, right? So again, we can make this thing as small as we desire, right? Right? Why? Because this is a character, right? And pi p to the n is pi p quantity to the n, right? So this is just the partial sum of the geometric series for that, right? Okay. So that we can make as small as we want, given control over m. And so the only one that we have to worry about is this one. Right? The only one that's a little bit complicated is this one. Okay. Okay. but this is basically the same. This is basically by the same argument that we had before, right? Using the fundamental theorem of arithmetic, right? This is the fundamental theorem of arithmetic argument. Right? Right, you just say, morning time, what? Is this how many times have you been injured?
Yeah.
Okay.
Yeah. They gave me an X-ray and I was thinking of the rad-on transform.
Yeah, that's saying I understand how this works.
Yeah, I was gonna tell her that, but she probably wouldn't care.
Yeah. Yeah. Can you write with that with your left hand? No. Okay. Well, there's video. You can watch the video, I guess. Yeah. Okay. Okay. So. Right. So sorry, I kind of forgot how this works. Let me think for a second. Right.
You just multiply inside the chi.
Yeah, use the multiplicativity of chi. Let me write it out. Sorry. For 2, you say, well, look, for each n less than or equal to n, you know that the prime factorization involves only primes less than or equal to n, and further, there are fewer than n of them. Right. And there are fewer than n of them. Right. So for n bigger than n, the right side, right, is the point, right? The right side contains all terms in the left. Sorry, the second term contains all terms in the first. Right? Does that make sense? That's clear. Right. The second term contains all, right? Because by multiplicativity, right? You're going to get all such n on the left hand side, right? Okay, and then right. So right, and so. Right, and since, so the terms not contained are in summation chi n over n to the s, where n is greater than n. Right, so you have some other terms there that won't occur here, right? Right, but this thing goes to 0, right? But this thing goes to 0 as n goes to infinity, right? So we can make this term as small as we want. Okay. Okay. So that's it for the product formula, right? Pretty straightforward. Okay. Any questions about that? Yeah, there's nothing really new in this argument. Yes, Jude.
I feel like when we prove the product formula for the Riemann zeta function in general, even though it should be exactly the same proof, Stein and Chakotchi didn't write up the details.
You think so? Like
I think they just said, well, look at the left-hand side, look at the right-hand side, and then follow.
No. I don't think that's. I don't believe. I'll take a look at it, but I think that one actually was that as simple as they presented it.
Okay.
Yeah, I believe so. But I will take a look at it to see if I can assuage your suspicions. Okay. Okay, so here is an observation that I think comes in handy later. So recall the trivial character chi naught of n was 1 if n and q were relatively common, and 0 otherwise. Okay, so the claim is that if we look at the prime factorization of q, so if q is p1 to the a sub 1, pn to the a sub n, is the prime factorization. Prime factorization of q, then the L function can be seen as, can be recognized as basically something times the zeta function. Okay, it's a zeta function times the product of 1 minus p1 to the minus s, 1 minus p2 to the minus s, 1 minus pn to the minus s. Okay. Which is pretty simple because, right, if we look at the L function, if we look at the L function for the trivial character, well, we just saw that that is, that can be written like this. Right? But we also know the zeta function can be expressed as 1 over 1 minus 1 over p to the s as p ranges over the primes. Right? So right? So the terms that are missing, right? The terms that are missing are exactly these terms, right? So that's it. Okay. So the missing terms are those corresponding to the primes that divide Q. Divide Q, right? In other words, P1 and P1. Okay, so that's just a minor observation. Okay, so if you think back to the Euler product formula and how it was used to get the infinitive primes proof, we needed to take the logarithm of both sides, right? We took the logarithm of both sides and then used facts about the zeta function to show that to get control of the terms, to get control over the sum over 1 over p one repeat of the s, right? So we're gonna do exactly that. Okay. We're gonna follow that strategy. We'll have to use a different we'll use a different log from the log. So the log that we used earlier, the log that we introduced earlier was based on the power series expansion of log, right? But this time we're going to, what we're going to do is express, we're going to define a second log, which I call log 2, and we'll define it as the integral, the negative integral of the derivative with respect to t. We'll get an integral form. We'll express the log as an integral. Okay, and that will be the expression that will come in handy when we try to get the control that we want, the kind of analogous control that we got before. Okay, so we'll use a different form of the log. In order for this to make sense, we actually have to prove some results about the L function. Yes.
Why do we negate the integral there?
Yeah. I'm not sure. I'm not sure, but. I'm not sure. Maybe that's a typo. Maybe it's yeah.
Where does in that expression was there no s or?
I think it was t. Oh wait, no.
Oh, I'm sorry.
Integral
It's from
0 to s.
It was from s. Sorry, it was from s to infinity.
Okay.
Sorry.
Ah.
Yeah. Sorry, I should wear my glasses. Yeah, of course. Thank you.
Okay. Questions?
Yes. Okay. So my glasses are on now. Okay. So in order for that integral to make any sense, we have to prove some stuff about the L function. So so here is sort of like a technical proposition. Okay. So let I be a non-trivial character. Then, the L function, which, of course, as you recall, is defined like this, right, actually converges for s bigger than 0. Okay. So we initially defined it for s bigger than 1. Actually, it converges for s bigger than 0. 2, L s chi is continuously differentiable in S. 3, for some constants, C and C prime bigger than 0, we have that Lx chi is 1 plus something of the order e to the negative cs as s goes to infinity. And 2, we have that the derivative with respect to s of the L function is of the order e to the negative c prime s as s goes to infinity. And this will allow us to talk about that integral expression. Okay, so So the first one we're going to deal with is this one, right? That when you take the sum over this, then it actually converges, and that hinges on the following observation. So first, observe that for any non-trivial character modulo q, then when you sum chi of q, chi of n, as n goes from 1 to any k, then that's controlled, that's always smaller than q. For any k. Okay. Right. And the reason is that, if you recall, when you sum from 1 to q, whenever you sum from, when you sum from 1 to q, you get 0, right? You remember there was this property of characters. When you sum over the group, you get 0, right? So summing from 1 to q will always give you 0, right? And further, this is periodic after that. So it's basically like every time you sum q things, you get back to 0, right? You get back to 0, and if you stop midway, well, each of these terms is smaller than 1, right, in absolute value, right? And so the worst you could have is q minus 1 terms, which is definitely less than or equal to q, right? Okay, right. So for any k equals a q plus b, where b is smaller than q. Right, we have that summation chi of n. Right. We have this. We go up to aq. Right, and then we have these final terms, right, from n equals aq plus 1 up to aq plus b. Right, and then this is 0. Right, so we could evaluate this, right, then we get it's equal to this, which is smaller than q times 1. Okay, so what that's saying is that we're taking advantage of the cancellation, right? This thing converges. This is not going to work, if the top is 1, right? But since the non-trivial characters have cancellation, we can get that this converges. Okay, so okay, so let's go for that now. Let's go for part 1 now. Okay, so proof of 1. Okay, so let me just say that let's show it. Show this for s between 1 and 0. For s bigger than 1, it's straightforward. And so we're going to use a trick. I've forgotten the name of the trick. sum by parts. So, okay, so using so-called sum by parts, summing by parts. So what you do is you let, you probably, if you've read through root and you've seen this argument, okay. So let S of k denote the partial sum, summation chi sub n from 1 to k. Let S naught be defined as 0. Okay. And then you say, well, then we can express, right, we're trying to, let's express the sum from k equals 1 the sum from k equals 1 to n as the sum of S of k minus S of k minus 1 over k to the s as k goes from 1 to n. Right? So we just take the partial sum up to k and subtract off the partial sum up to k minus 1. That gives us the top term, chi of k. Right. And then that we split into two sums. S of k over k to the s, k goes from 1 to n, right? Minus summation s k minus 1 k to the s as k goes from 2 to n. Right? Remember that S0 is 0. Right? And then we rewrite this guy. We rewrite the term on the right as we just change the index so that it goes from k equals 1 to n minus 1. So sk over k plus 1 to the s. Right. And now we combine them together. We take the top term out, and then we combine these guys together. Right. So the top term is s of n over n to the s. And then we combine these guys together. So we get summation k from 1 to n minus 1 sk 1 over k to the s minus 1 over k plus 1 to the s. Okay, which we rewrite. We write this as summation k equals 1 to n minus 1 f sub ks plus this last thing, s of n over n to the s. Finish up this one by partial sums. That yes. Okay. Sorry. 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 Got confused for a second there. Okay. So right. Okay. So okay. So now okay. So now. Yeah, so now consider the absolute value of fk of s. Okay, that is s of k 1 over k to the s minus 1 over k plus 1 to the s. Right. Okay. And each of these, by what we just said, the s of k are controlled by q, right? So this is less than or equal to q times times this difference, right? But by the mean value theorem, this difference is controlled by, right, the maximum of the derivative of x to the minus s as x ranges between k and k plus 1. Right? So this is this part by the lemma, and the second part by the previous lemma and the mean value theorem. Which equals qs times 1 over k to the s plus 1. Right? Because the maximum is going to occur in k. Okay, so what does that give you? That gives you that and remember s is between 1 and 0, right? So we have these guys are controlled by 1 over k to the s plus 1 in absolute value, right? And so we see that so summation fks as k goes from 1 to infinity converges absolutely. Right, and also converges uniformly on s bigger than some delta, bigger than 0. Okay, right. And then, so this converges, right, absolutely as n goes to infinity, right? And that gives us the convergence that we wanted, right? We were trying to show that that this thing converges for s bigger than 0 as n goes to infinity, right? And so we get it, right? You also have this term, but this term is bounded by q, and this goes to infinity, so this will vanish. Okay, so so we get that this is right. So we have so we have that the sum is actually continuous. And then so part two is similar, right? Showing that you can showing that the function is continuously differentiable is basically same sort of argument. You just differentiate term by term, and you just do the same sort of argument. And then part 3, right, so to get the, right, so remember part 3, we wanted to show that LSX was 1 plus something of the order e to the negative cs, right? And that's actually pretty straightforward. You say, well, for s bigger than 1 plus epsilon, we have that L of Sx minus 1 is, by definition, summation I of n to the s as n goes from 2 to infinity. Right. The term is 1 when n equals 1. So we just take off the initial term. Okay. But that is controlled by the integral of x to the minus s dx from 2 to infinity. Right. So placing absolute value is controlled by this. Okay. But that just equals that equals 2 to the minus s times 2 over s to the minus 1, which is less than or equal to 2 to the minus s times something of order 1. Okay, so it's just a calculation, right? Right. Yeah. The difference between this and 1 is this, which is bounded by this thing, which is this, which is basically e to the negative cs times something of order 1. So that's that. And then the second bound is proved similarly. Okay, so this is all so that we can talk about the logarithm as that integral, and then once we have that will actually then we'll be able to get a logarithmic version of the product formula, and then that will give us the result modulo. So, or at least that will reduce the problem to a different problem, which will take us a couple days to finish. So yeah, I think there are probably 1 or 2 more days of lecture for Dirichlet theorem, but it'll feel good once we get there. Okay, that's it.